Good morning. The topic of today in the 8th lecture on model checking is regular properties. So what we have seen so far are properties which were linear time properties. On the other hand, we have seen transition systems. Here the idea is that these properties, they play the role of a specification. So these specify the properties that the system should exhibit, preferably. And the idea is that the transition system is basically a model of a real system. Being it a program, being it a parallel composition, so multi-threaded programs or whatever, or something like a Promula model. And now the idea is that we're going to bring these two things together, and they are going to be the inputs to model checking. So if this is a property, let's say phi, if this is a transition system Ts, model checking is going to check whether Ts satisfies phi or not. Yeah, and preferably there are two possible outcomes. Either it says yes, the transition system satisfies your linear time property, or it says no, which means the transition system does not satisfy the property, and then you would like to have something like a counterexample. So what we are going to do today is we're going to see the very first elementary, simple model checking algorithm. And in order to do that, what I'm going to do is I'm going to focus on one specific type of property, and they are called regular properties. So I'm not going to talk about linear time properties in general, but we're going to consider regular linear time properties. And what we're going to see is that actually we can use old-fashioned automata theory for doing the model checking for this specific type of property. And either at the end of today or otherwise in the next lecture this week, I'm going to enlarge this set of properties, and then we're going to see that finite state automata are not sufficient anymore, and we need another automata model, which we are then going to introduce, which are called Buggy automata. So for today, I'm focusing on what we call regular properties, and I'm going to explain you what that actually means. Actually, what we're going to see is that regular properties are a subset of safety properties. So maybe you remember the diagram I drew last lecture. This is the spectrum of all LT properties. Here we have safety. Safety includes all invariants. We have seen that there is liveness. There is one property which is a safety property and a liveness property. This was the property 2 to the AP omega, which is the same as saying true. This was both a liveness and a safety property, and what we have seen in the last lectures is that any property which is here is actually equivalent to a safety property and a liveness property. So a conjunction, or if you turn it into sets, it's an intersection of a liveness property and a safety property. An intersection because properties are sets of traces. What I'm going to talk about today are regular properties. And regular properties are a part of safety properties, and we're going to see that this is the kind of properties we are going to consider. As we're going to see, they include the invariants. They include some of the safety properties, but not all of them. And these are called regular. And the reason why I'm doing this is that I can use off-the-shelf automata theory to do the algorithms, and that gives hopefully a kind of hopefully easy introduction to the first, simple, but the first model checking algorithm. And then we're going to enlarge this so that in the end we're going to cover all properties here, but that requires a little bit more machinery. Okay, so what's a regular property? A regular property is a language of infinite words. That's not surprising because every LT property is a language of infinite words. It's a set of infinite words over the alphabet 2 to the power AP. And the idea is, and that's the most important point, that have a representation by a finite automaton. A finite state automaton that you are all hopefully familiar with. I will do a short recap because I have to introduce my notation, but standard finite state automata. Good, so what's the idea? We're going to focus on regular safety properties. And remember what was a safety property? A safety property can be shown to be violated by means of a finite bad prefix. And if you consider all the finite bad prefixes for a regular safety property, they can be represented by a non-deterministic or a deterministic finite state automaton. We're going to see for the other properties that we're going to call regular, we need other kind of automata, because there we need automata for infinite words. Today we're going to stick to automata accepting finite words. Good. So just recap, I'm not going to the whole definition again. What was a safety property? A safety property means that if I give you a finite, an infinite word that is not in the safety property, that means this is an example which does not belong to the property we are considering, then this has a finite prefix, which we call a bad prefix, such that none of its extensions are actually belonging to the safety property. So no matter what you put after this finite prefix, B's, then actually you never get a property which belongs to E. And this is written down like here. If you take the set of E and you intersect it with all the infinite words that are extensions of this bad prefix, then this is the empty set. Good. And we use the notation badpref for the set of bad prefixes of a property. So what's a regular safety property? So first of all, I fix E to be a set of infinite traces. So E is a property, and it's a safety property. And we call such an E a regular safety property if and only if the language of all the bad prefixes is a regular language. Yeah. And that means in particular that you can represent the set of bad prefixes by means of a regular expression, or equivalently by means of a non-deterministic finite state machine, or equivalently by a deterministic finite state machine, because all these three are equivalent. So that means that the set of bad prefixes can be represented by the language of some non-deterministic finite state machine, and the alphabet of this non-deterministic finite state machine is 2 to the power AP. Why is it 2 to the power AP? Well, it needs to recognize all the bad prefixes. Bad prefixes are finite words, and every symbol in the word is a set of atomic propositions. So the kind of symbols that my automaton has on its transitions are sets of atomic propositions. Good. So a brief recap, and that's only in order to introduce my notation for non-deterministic finite state automaton. We have the usual ingredients. So a finite state automaton is a quintuple. It consists of a finite set of states. We have an alphabet. We have a transition relation, or here a function that takes the current state, takes the next input symbol, and tells you which are the possible next states. Notice that this is the power set of Q, so that it's a non-deterministic automaton. We can have a couple of initial states, Q0, and we have a set of final states, or accept states, which is also a set of states. we have the usual things. We have a run, so we can feed the automaton with a word. This word is a finite word, something of the form A0, AN-1, which of course belongs to the alphabet, so it's a string in the set sigma star. And then the idea is that a run for this word is a state sequence, so it's a sequence of states in my automaton. This contains one state more than the number of symbols in this word, such that we start in some initial state. Q0 belongs to the set of initial states, and there is a transition in the automaton labeled with the next input symbol that leads you from the current state Qi with the next input symbol Ai to the next state Qi plus 1. Good. That's the ordinary standard acceptance condition of automata. And we call a run accepting if the final state, so if Qn, the final state of the run, is an accepting state. Good. What's then the accepted language of the automaton? This is the set of finite words for which it has an accepting run. And I call this L of A. Good. In my setting, the alphabet is, as I said, we are interested in automata that accept bad prefixes. A bad prefix is a finite word over sets. So the symbols in my alphabet are sets of atomic propositions. So formally, sigma, in my case, is the power set of AP. Good. So here is my notations. So here is an automaton with two states. I use this incoming arrow that comes basically out of the blue as an initial state. Then there are the circled state are the states that are non-final, so non-accepting, and the boxed states are the final states. So this has one non-accepting state and one accepting state, and apparently the input alphabet is capital A and capital B. Good, so this is an automaton with two states, Q0 and Qf, with one initial state, one final state, and the alphabet is AB. What's the accepted language? Well, that means that we have to see at the accepted runs that end in this state, okay? So in this case, it's the set of all finite words over the alphabet that end with the letter A. Why do they have to end with the letter A? Well, there is only one possibility to end in this state, namely that you have to take an incoming arrow labeled with capital A. Either because you go from Q0 to Qf, or you take the self cycle. Yeah? And there is no restriction on actually taking any A's and B's in the beginning, so therefore you take any finite word, but it needs to end with an A. Good. I will use some notation. Why do I use some notation? Because it's a bit awkward to always equip a transition with a set of atomic propositions. I prefer to use simply logical formulas to do that. So I'm going to use the following notation. I'm going to take phi to be a propositional formula over the atomic propositions as a shorthand, and that means that if I have a transition from state Q to state P labeled with the propositional formula phi, this transition is a symbolic representation of a set of transitions in my automaton, namely for all the transitions from Q to P labeled with some set A, so A is a set of atomic propositions, such that this set satisfies the formula phi. Okay, I do this only for the sake of convenience, otherwise you have to write down many transitions. Some example, suppose that I have the alphabet, well, not the alphabet, the set of atomic propositions being A, B, C. That means the alphabet of my automaton will be 2 to the power A, B, C. Now suppose that I now write down a symbolic representation that I can move from state Q to state P with the formula A and not B. This means this is a symbolic representation of all transitions between Q and P, from Q to P, to be precise, that with sets that contain an A and do not contain a B. Okay, so formally, it's the set of transitions from Q to P where A is a subset of ABC that contains an A but no B. What are the sets satisfying this? Well, this is the singleton set A as well as the set AC. Okay? So in my case, in this example, this is symbolic representation represents two transitions. So it is a shorthand to just, instead of drawing two transitions, I just have to draw one. Yeah, that's the idea. I hope this is clear. What does this mean? Q to P with the formula true. True actually is a formula that is always true, and that means this is a symbolic representation for all transitions between Q and P labeled with some A, where A is a subset of AP. So in my case, this is, for instance, labeled with the empty set, the singleton set A, the singleton set B, the singleton set C, etc. Right? So here this represents about 2 to the power 3, which is 8 different transitions. Okay, good. I hope this is clear. So what we're interested in is this bad prefixes. Remember, a safety property is regular if the set of bad prefixes is a regular language. So here is an example. This is a non-deterministic finite state machine over the alphabet AP. It's non-deterministic. Why is it non-deterministic? For instance, in the state Q0, we have a self loop with true, which means this is representing a set of transitions labeled with all possible sets. But in addition, there is a transition to Q1 with A and not B. Yeah, so if in state Q0 the next input symbol is a set containing A but no B, there is a non-deterministic choice between either taking the self loop at Q0 or moving to Q1. In this state, we move with A and not B to Q2. And in Q2, actually, we are able to consume any next input symbol, and we will stay in Q2. Okay? What's the language accepted by this automaton? Yeah? It's an automaton for the bad prefixes, right? So it means that we are going to accept, so that's a symbolic notation, A and not B means simply the singleton set A, right? Because that's the only set that is containing in satisfying the formula A and not B. And this is the safety property that A and not B never hold twice in a row. Yeah? I mean, A and not B hold once, A and not B hold twice. That means this automaton accepts the word that we get A and not B twice in a row, but it's a bad prefix, so it's a property that we don't want to see, so you take the negation. Yeah, that's the idea. So that's why the never comes in. Yeah. Any other property is fine, but this bad prefix automaton says A and not B never hold twice in a row. Good. What we will be confronted with is the following. In a minute, we will have a finite transition system. So here we're going to restrict ourselves to being finite. We have a regular property, like the one here. A and not B never hold twice in a row. How can we algorithmically check whether any arbitrary finite transition system satisfies this property? Yeah? Or a given finite state transition system satisfies this property. And then, of course, we would like to be able to do that for any possible transition system. Another example of a regular safety property for a traffic light, every red phase is preceded by a yellow phase. Yeah, so if the light turns red, it should have been immediately before yellow. Good, so that is formally written down as a property as follows. It's the set of infinite words, A0 up to etc., such that for every position, if red is contained in the ith position, then it should not be the first position, so I should be strictly larger than 0. And yellow should be in the immediately preceding position, A minus 1. AI minus 1, sorry. Good. This is a regular property, it's my claim. So this is a property whose bad prefixes are represented by a regular automaton, and this is an automaton. It's actually a deterministic machine for all possible bad prefixes. So let's look at this automaton. What would be a bad prefix? Well, a bad prefix would be something that red is immediately true in the very first position, 0. That means that in this automaton we start in Q0. If red is contained in the the first symbol of your input word, you go to QF. That means it's bad. Yeah? The automaton accepts. What otherwise is bad is something that you have red and it's not preceded by yellow. So here you see that, okay, if it's yellow, you go here. If it's still yellow, it's fine. If it's not yellow, it's there. And that's still accepted. That's all okay. Yeah? So not yellow means in particular also the state, the input symbol where you contain red. Yeah? And this is all fine, which means you do not accept this. Yeah? That's all fine. Okay. Good. So you start in this input state. If the next input symbol is something like the empty set, you take the self loop. Yeah. If the next input symbol is yellow but not red, you move to the left state. So that means you just have seen a yellow light. If you then see another yellow light, you stay there. But if you see something which is not yellow, then you move back to Q0. Good. So what happens is that you are in Q0, you just have seen not yellow. If then red comes, it's bad. Yeah, because according to the property, red should only occur if yellow has been true in the previous, immediately preceding input symbol. Good. This was the automaton for all bad prefixes. If you would like to have all minimal bad prefixes, that's quite simple. Minimal means that you only accept those bad prefixes that do not contain bad prefixes. And what you see here is this automaton can accept a bad prefix, but then can still continue and still accept a longer bad prefix. If you would like to avoid this, then you just remove the self loop. And now you have an automaton that accepts all the minimal bad prefixes. Yeah? The shortest, if you want, the shortest prefixes that are showing that the safety property is refuted. Okay. It's very easy to show that if the set of bad prefixes is a regular language, if and only if the set of minimal bad prefixes is regular. So it doesn't make a difference whether you consider regularity on the level of bad prefixes or on the set of minimal bad prefixes. Why is this? Well, if you give me an automaton for the minimal bad prefixes, so assume that the minimal bad prefixes are regular, that means there exists an NFA for this set, then you can obtain an NFA for the bad prefixes by simply adding self loops of the form P through P to all the final states. That means once the minimal bad prefix automaton accepts, you can still continue by accepting any extension of the bad prefix and still saying it's a bad prefix. Vice versa, if you start with bad prefixes being regular, assume that there is a DFA for bad prefixes, and then the DFA for the minimal bad prefixes is obtained by simply removing all the outgoing transitions of the final states. That's exactly what I showed you on the previous slide.
So if you say we obtain a DFA, then you do not require DFAs to be complete in your...
I come to this, yes. Yeah. We are going to assume that for the theorem, I have to assume that my automata are complete. I will get to this. I call this total, but it's the same as what you call complete, yes. So every invariant is regular. Why is this? Well, you take an invariant with an invariant condition. Remember what was an invariant? Invariant was specified by a propositional logical formula, phi, that holds at any position along a word. Yeah. So is this regular? Yes, because here is the automaton for the bad prefixes. It's just a two-state automaton. As long as the invariant holds, it's all fine. It's not bad. But as soon as you reach a position where phi does not hold, you move to the bad state, to the accepting state, because then you have encountered the bad prefix. This is an automaton. It is easy to see that this represents all the bad prefixes of an invariant with condition phi. So this is regular. Yeah? And this is also indicated by this diagram over here. The regular properties contain all the invariants. And here is the minimal bad prefixes. You just remove the outgoing edge of Q1. Two processes are never simultaneously in their critical section. This was the mutual exclusion property that will be useful for the algorithm with the binary semaphores, the Peterson's algorithm, and so forth. So what's a DFE for the minimal bad prefixes? They look as follows. You take as atomic propositions the set crit1 and crit2. Why do I take this set? Well, we have to look at the property that we want to specify, and the set of atomic propositions of the set of the bad prefix automaton needs, of course, to cover all elementary elements of the property I'm interested in. Yeah? So here I need to show that a process can be in the critical section. So I do this for process 1 and I do this for process 2. I could extend this alphabet with weight, with non-critical, etc., but for this property it suffices to only look at crit 1 and crit 2. So this is an invariant. It says it's never the case. So that means that my bad prefix automaton looks as follows. If only one of the or none of the processes is in the critical section, we stay in this state. But as soon as both processes are in the critical section, we move to that bad state because that's the situation that we typically would like to avoid. Okay? Good. So this is also a regular property because it's just an invariant. Every safety property is regular. This, of course, I hope you immediately see this is nonsense. Why is this nonsense? Because you can also specify things which are not regular anymore. So here you have an example. The set of all infinite words such that, and this means the cardinality of the set of positions along the word that contain the word pay is at least the cardinality of the set of positions that contain drink. So this basically says the amount that you paid is at least the number of drinks that you obtained. Yeah. And this means that you need some kind of counting argument. And this counting, as you all know from automata theory, is not regular. And therefore, this is an example of a non-regular safety property. So this is an example of a property which is here. Yeah? So this is typically something which is non-regular. And in this case, it's context-free. Yeah? Good. So it's good to understand that we really have a quite severe restriction today. We only consider those regular safety properties. But as I said in the beginning, I do this for the sake of simplicity and for the sake of introducing this first, let's say, simple model checking algorithm. Good. It's of course a safety property, but it's not a regular language. So what's the idea of verifying regular safety properties? So what are we going to consider is the following. We're going to consider the following problem. Given a finite transition system, a regular safety property E, and how are we going to deal with this regular safety property? We're going to represent the set of bad prefix by an NFA. And the question is, does T satisfy the regular safety property? And that's what I would like to do by means of an algorithm. So the method relies on an analogy between the following two tasks: checking language inclusion for NFAs and model checking of regular safety properties. We're going to see on the next slide that those two problems are very strongly related. Good. So here I have a slide where in the left column it's the language inclusion for NFAs. On the right column it's the strategy that we're going to pursue, and I'm going to detail this in the next part of the lecture to verify regular safety properties. So here the question is, given two NFAs, is the language of automaton 1 included in the language of automaton 2? And you see there is a similar question here. Here we have a set of traces of a transition system, and we are requested whether it satisfies E. And you remember that satisfying E means it's the same as that these traces are a subset of the set of properties we are interested in. So these two questions look very similar. Now, how are we going to check that whether A1 is included in A2? Typically what you do is you look at the intersection. So you take the language of A1, you take the complement of the language of A2, and you check whether the intersection is empty or not. Yeah? Good. How do you do this? Well, you complement A2, that you construct some NFA where the language of this complement is exactly the complement of the language of A2. I hope you all remember that you can do this by means of a standard construction. In particular, for a deterministic finite state machine, you can just flip. You can just inverse those states which are non-accepting becomes accepting, and those accepting states become non-accepting. So that's a very simple procedure. Then you construct an NFA that actually accepts now the intersection between the language of the first automaton and the language of the complement of the second automaton. And then you check whether this automaton, so this language, is empty or not. Yeah? Because that means that we have checked whether this is empty or not, and we can finally answer the question, is A1 included in A2 or not? The intersection is empty, this is not the case, and otherwise, etc. So how do we do this here? We're going to do this in a very similar manner. We're going to check whether the finite traces, so all the finite behaviors exhibited by the transition system, can never expose a bad prefix. That means the intersection with the set of bad prefixes, of E, of course, is empty. How are we going to do this? We're going to construct an NFA for the bad prefixes. In some sense, you can consider this as the language of the complement of the safety property that you are considering, right? Because the automaton accepts everything which does not belong to A. Then we're going to construct a transition system similar to the automaton here, such that this transition system is going to accept basically the intersection of the finite traces of T and the bad prefixes. And then I'm going to show you that rather than checking whether the language is empty, we can reduce checking whether a regular safety property holds by checking an invariant on the new transition system. Yeah. So what's the recipe? You give me a regular safety property. I give you an automaton for the bad prefixes. We're going to combine this automaton with the original finite transition system. This gives us a new transition system, T prime. And then I'm going to argue that in order to check whether my original transition system satisfies the regular safety property, it suffices to check an invariant on the new transition system. How can we check an invariant? Depth first search. No, that's something we have seen before. Good. Okay, now we go to the through the right column step by step. And basically here I have a visualization of what we are going to do. Here is a finite transition system and a regular safety property. I'm interested in the question, does T satisfy E? And what we are going to do is the first step. For the regular safety property, it's easy. I mean, it's regular because so we can construct a bad prefix automaton. So the input to the algorithm will actually be this bad prefix automaton and the finite transition system. And then what we're going to show is that we're going to construct a new transition system, which will be some kind of combination of the non-deterministic finite state automaton and the transition system. And in this new transition system, we're going to check that we can never reach a final state. And what's the intuition of this? This is the kind of a synchronous product. So that means that the behaviors of this T cross A transition system are those behaviors that the original transition system have and the automaton has as well. And then if this, let's say, it gets to a final state, that will be bad. So we're going to check that this new transition system will never reach a final state, will never allow the bad prefix automaton to say accept, because that would mean a violation of my property. Good. Okay. And we're going to see that it does not only yield the answer no, it also gives you something like a counterexample. Why is it violated? Good. Are there any questions on this roadmap? No? Good. So the first thing I'm going to introduce is this synchronous product, the product of a transition system and a non-deterministic finite state machine. The intuition is that we would like to construct a transition system that exhibits all behaviors that are basically possible by both components, by TS and by the non-deterministic finite state machine. So the idea is the following, and this is the intuition, and then we get to the formal definition. So we take a finite transition system, and let's suppose that here is a path in this transition system. So I can start in some initial state, then I can move to S1, I can move to S2, etc. The symbols on the transitions here are not so relevant. On this side I have an NFA for the bad prefixes. This has the usual ingredients, and remember the alphabet is 2 to the power AP. Why is this important? This is the same AP as the transition system has. So these states here, S0, S1, etc., are labeled with sets of atomic propositions from AP. And those sets we're going to use in the automaton. So this is visualized as follows. So I look at the label of S0. This is a set of atomic propositions, and I just represent it here symbolically by A0. Similarly, S2 is labeled with A2 and so forth. Good. Now, these symbols are going to play a role in the non-deterministic finite state machine. So here is a run of the finite state machine. This run starts in some initial state of the finite state machine. Then it moves to some next state Q1 by actually reading A0, which is this A0. Right? Then it moves to Q1. Then it can evolve to Q2. How can it do that? By reading this A2. Yeah. So what I'm going to do is that here I'm going to use state labels in my transition system, and I'm going to use them as transition labels in my automaton. Okay? That's what I'm going to match one by one. Good. So this looks as follows. So basically here you see this A0 is consumed here, this A1 is consumed there, this A2 is consumed there, etc. In my product construction, what I'm going to do is what is represented in the middle. I'm going to build pairs, but I'm not going to build a pair with S0, Q0, but with S0, Q1. Then with S1, Q2, etc. to be able to represent that those two states indicated with the dashed line, this state in my transition system, this state in the automaton, belong together. Yeah? Good. So this is a trace in my transition system. This is a run in my automaton. If my automaton accepts, then this trace is bad because it violates my safety property. Good. So let's now define this, and then I move to an example. So the product transition system is defined by a transition system and an NFA. And the product is just a Cartesian product of the state space. So I take really S times Q. And I take a set of actions, which is the set of actions of the original transition system. So that's not changed. And I have those four components that I have to define in a minute. So this is the transition relation, and this is the most important part of it. If my transition system can move from S to S prime with action alpha, and if in my automaton I can move from Q to Q prime by reading the next input symbol. What is the next input symbol? It's a set. Which set? Well, it's the label set of the target of this transition. It's the label set of S prime. Then the product automaton can move from SQ to S prime Q prime by again doing action alpha. Yeah, so what is the important ingredient is that this transition system moves to S prime. Intuitively speaking, the label set of this S prime is used as input symbol of my automaton, and if my automaton then, by consuming this input symbol, can move from Q to Q prime, the product can move from SQ to S prime Q prime. What is a set of initial states? Remember, we don't start in S0, Q0, but in S0, Q1. How is this defined? I start in S0, Q, where S0 is an initial state of my transition system, and Q is a state that I can reach from some initial state in my automaton by already consuming the labeling of state S0. Good. What does this mean? This is a generalization of the notation delta Q, but this is just a generalization for a set. So this simply means if I have a set P here, it's the union over all states in capital P of the transitions of small p. So it's just a pointwise extension for a set. Set of atomic propositions, I'm going to label the states in my new transition system actually with the states of my automaton. I'm keeping track of which states I'm going to basically follow in my automaton. And that's the labeling. So if I have a composite state SQ, the label is just the singleton set Q. Good. I think the easiest way to understand this by means of an example. So here is a very simple transition system and representing a very simple traffic light. We start in the green state. It can move to yellow, it can move to red. Then it moves to some state, well, in between red and yellow apparently. And this is labeled with empty set. That's labeled with empty set. This is labeled with the singleton set yellow, and that's labeled with the singleton set red. That's indicated by the colors. It's hard to see for you, but that's indeed red, and that's supposed to be something like yellow. What's the property we are considering? So I'm interested in checking the following property. T satisfies the safety property. Every red phase is preceded by a yellow phase. Now, this for us is easy to see because we look at the red phase. Red only holds here. Then this is preceded by a yellow phase. That's true because you can only reach that state by passing through that state before. So for us, it's obvious to see that this property holds. That's, however, not the question. The question is, how can we do this by means of composing it with the bad prefix automaton? So we're going to take the automaton for the bad prefixes of this property. What is the bad prefix automaton for that property? Well, that's exactly the automaton we already have seen before. Now, this was this automaton that said, okay, if the initial position is red, accept, because that's bad. If the previous position is not yellow and the next one is red, that's also bad, because that also violates my property. Good. Now I'm going to build the product of this transition system with this automaton. Good. So let's do this. So this has states are the Cartesian product. So I get 4 times 3 states, which are 12 states. I only represent basically the beginning. So possible states are something of the form green Q naught, red yellow Q naught, yellow Q1, etc. So now let's look systematically how I get to my product construction. So the first is the initial state. What is the initial state? It's the combination of the initial state in my transition system. I look at the label of that transition system, of that state, which is the empty set. I now look at the initial state of my automaton. I feed the automaton with the empty set. What happens? In this case, I take the self loop, and that means I stay in Q0. Okay? So this is here. I consider green, and I consider delta Q0 empty set. So what is the state after feeding the automaton with the label of my initial state? Good, that's green, and that's Q0, and that means that this is the initial state of my product. Good, let's continue. Now we consider this edge. So we consider the edge in my transition system from green to yellow. So what was the rule? The rule in the definition says the following. The rule says if S can move to S prime by means of some action, but the actions are not relevant here, and if we know that you are in some state Q, and we take the label of S prime, then let's say we take Q prime, yeah, if that's included here, then I can take a transition from S to Q to the pair S prime Q prime. Yeah, that's the rule. Where is my pointer? Ah, here. Thanks. Good. So if we apply this now on the following thing, so we're considering green goes to yellow, then means that we are considering the transition of green, comma, well, where are we now? We are in Q0, so we consider green Q0, and we're interested in what is the resulting state. So what's the state Q prime? That's actually the question. So what are we going to do? You just consider the current state green, the current state Q0. You feed it with the input symbol, which is the labeling of yellow. What is the labeling of yellow? That's the singleton set yellow. Now feed it to this automaton. So we are in Q0. The next input symbol is yellow, this singleton set. That satisfies this criterion of this transition, and therefore we move to Q1. So what we get is we get a transition to Q1, and that's represented in the product like this. And this scheme continues. So for instance, now we consider the transition from this state yellow to red. So we consider this edge in the transition relation in the left transition system. We are currently in the state yellow Q1. We feed the state Q1 with the label set of red, which is the singleton set red. What is the transition? We take the automaton. This is this transition, so we move back to Q0. So this is the transition. And if you complete this, then actually we move here from red to the state red-yellow, which is this transition here. This is labeled with empty set. Feed this state with empty set. That means you take a self-cycle. And that means from red-yellow Q0, we go from red Q0 to red-yellow Q0. And if you continue this, then you look at this edge, and that means you have to feed Q0 with the label set of green, which is empty set. Again, we take the self loop, which is green Q0. So what we see here is that out of the 12 states, 4 times 3, only 4 of them are reachable. Yeah, in this example. Good.
So right now, sorry.
Yeah.
If the case now the product TS is the same as the TS, as our original TS?
Well, that's a coincidence here. That's a coincidence here. That it looks very similar to the one before. That's a coincidence.
Okay.
Yeah, I mean, of course, those 8 states are still there. I didn't draw them because I was a bit lazy. I only drew the reachable ones, but they still belong to the same thing. Yeah?
Correct.
And the states have a different structure, right? I mean, yeah. Good. Only 4 reachable states. What are the set of atomic propositions? The set of atomic propositions are the states of the automaton. So what's the labeling of this thing? Well, you just can ignore the first component in every state, and then you have the labeling. And now my claim is that in this transition system, you can never reach an accepting state. Yeah? There is no reachable state where the second component is QF. What does that mean? It means that the transition system has no bad behavior. It can never generate a bad prefix. Formulated positively, it satisfies the safety property. Yeah? How can I check this? Well, I can just check, is there something reachable here that is accepting? And the answer is no. Good. So I can take an invariant condition, not QF. Is not QF an invariant? Saying the same as it's never possible to reach a bad state. Yeah. And this is satisfied in all those states, and therefore this invariant is true. Good. Some technical remarks, and this is the remark that has been made before about completeness, or at least part of it. So actually the definition, if I take a transition system NFA, then the product is typically a transition system. In particular, this holds if the T has no terminal states, and that's the typical situation we are considering, that T has no terminal states. So that means that every state has at least one outgoing edge. And then this also has no terminal states. What are the assumptions we're going to make on the NFA? We're going to make 2 assumptions. A is non-blocking, or what you call complete. Non-blocking means there is at least one initial state. And for every state in my automaton, for every possible next input symbol, there is a transition. You call this completeness. It's non-blocking. And the second thing is no initial state is final. That means I'm going to assume that the intersection of the initial states and the set of accept states is empty. Why do I do this? Because a bad prefixes being the empty prefix is not a valid bad prefix. So I would like to exclude the fact that my bad prefix automaton is accepting the empty word. Good. So here is an example of a non-blocking or incomplete NFA. Is the alphabet AB. Now, if you, for instance, look at this edge and then you take this edge, that means you have just inputted the word, for instance, singleton set A, then empty set, so you have taken the self cycle, and now the next input symbol is something like singleton set A. This has no outgoing transition there, so this is not complete or not total, or in my terminology, non-blocking. So the easy way to fix this is basically to introduce an extra state, which we call stop here, and we're going to basically for every non-blocking state, we're going to add a transition. So in particular, this state, I do not have a transition for the set A, so I'm going to add a transition that moves to the stop state from A, and from this stop state only has a self loop, so you can never reach an accepting state from there. So this is what happens. You see that this also is not complete because it only has a B transition. What happens in this state if I have a next set which does not contain B? Well, intuitively speaking, it goes to this stop state. I'm just assuming from now on that my non-deterministic automata are non-blocking. And this slide tells you that every non-blocking NFA can be transformed into an equivalent, every blocking NFA, can be transformed into an equivalent NFA which is non-blocking. Good. What happens if I have an initial state? So suppose my original automaton looks like this. I have an initial state which is also an accepting state. Then one way to do this is that you can transform this into the following automaton. You make a copy of Q0, which is Q0 prime. That is non-accepting. And you basically redirect the outgoing transition. So you have this A and B transition that moves to P. Now this one has an A and B transition that moves to P. This one has a non-A transition to R. So this has a non-A transition to R. And the rest of the automaton stays the same. Yeah, so I literally only made a copy of Q0 here. And that's it. Then it's clear that this automaton does not accept the empty word. So this automaton is an NFA which is strongly related to this one, except that it does not accept the empty word. As I mentioned, there is a technical reason for avoiding the empty word, because the empty word is not a valid bad prefix. Yeah? Good. That's written down here. If A is an NFA for the bad prefixes of a safety property, then we know that epsilon, the empty word, should not be in the bad prefix automaton, not be accepted by this automaton. Good. So now I get to the model checking of regular safety properties, and we're going to reduce this to invariant checking. So I'm going to assume that I have a transition system T, finite transition system, and we have this bad prefix automaton A for some regular safety property E. And I'm going to assume that this has no terminal states, and I'm going to assume, without loss of generality, that this non-deterministic finite state machine is non-blocking. Remember, if it's blocking, I can transform it in something which is equivalent but non-blocking. And I'm going to assume it does not accept the empty word. Yeah? Because of the reason I mentioned before. Good. Then the following statements are equivalent. Actually, I have three statements, and this is what I'm going to show on the blackboard. T satisfies the safety property if and only if there is no finite trace of T which is accepted by the bad prefix automaton. This is relatively easy to see that 1 and 2 are equivalent. But the important point is point 3. 1 and 2 are also equivalent to the third statement that says the product of T and the bad prefix automaton satisfies the property that the invariant property that always not f holds. Phrased differently, you cannot reach an accepting state in the product. That's what it says. Yeah. Good. So this is the question we were originally confronted with. Does T satisfy the regular safety property or not? Thanks to this theorem, which I'm going to prove in a minute, we can reduce this to the question whether the product satisfies an invariant. And we know an invariant checking is easy. It's a depth first. This can be done in linear time. Well, linear in the size of this product. Yeah. So what I would like to show is basically I'm going to claim that 1 is equivalent to 2. That's pretty straightforward. And actually that's left as an exercise. So I'm going to consider the other cases. So the first case I'm going to consider is that 2 implies 3. In fact, I'm going to prove that not C implies not B. So let's assume C does not hold. Yeah, so I start from here, and that means let TSA violate the property always not F. What does that mean? Then this transition system has an initial path fragment, so a finite path starting in some initial state. Let's call this the following path fragment: S0, Q1, S1, Q2, dot dot dot, Sn, Qn plus 1, such that Qn plus 1 belongs to F and Qi does not belong to F for all 0 less than I up to n. Yeah, because it violates always not F, there needs to be a finite path that leads to an F state. That's basically what this says. And this is the structure of such a path in the thing. Besides, we know the following. By construction, or by definition of this product, we have that S0, S1, Sn is an initial path fragment in TS. So what I'm saying here is if I only consider the first components, right? S0, S1, Sn. So this is my S0, S1, Sn. This is an initial path fragment of TS. And if I only concentrate basically on those second components, then I know that this is actually ending in a final state. And actually I know more because it means that my automaton has a run. So moreover, we have that Qi can move to Qi plus 1 by the label set of Si. Yeah? So now what I do here is I concentrate on these components, q1, q2, qn plus 1. Yeah. And I know that from qi, I can move to qi plus 1 by taking this label of Si. Why is this? Yeah, otherwise this would not be a path fragment in the synchronous product, right? Synchronous really means, by definition, that the yellow, let's say, word is really an initial path fragment of the transition system. And if I take the blue sequence, this is a run, and actually an accepting run of my automaton. So that means there needs to be transitions of this form in my automaton, otherwise this would not be a run. And this means for all I for the rest, as S0 Q1 is an initial state, it means that Q0 has a transition to Q1 with L as 0 for some initial state Q0 in A. Thus, altogether, we know that Q0, Q1, Qn plus 1 is an accepting run. Of A. For what? For the finite word trace S0 Sn. What is this? This is exactly L S0, L Sn, L Sn. Thus, this trace belongs to the intersection of the finite traces of Ts and the language of this automaton, and that means that this thing is non-empty. And that's exactly what we need to prove, because that's exactly not B. Yeah, so a short recap. We need to prove 2 implies 3. Go back one step. It's on the top slide there, 2 implies 3. So the traces intersected with LA is empty implies TS cross A satisfies always not F. I proved the opposite. So I start with not B. We then have that there is an initial fragment in this composite transition system. I analyze this in detail. Then I can conclude that there is an accepting run of this automaton. It's a special accepting run because the accepting run is exactly for the finite word the trace of the corresponding state sequence in the transition system. And that means that there is a finite trace which is accepted by the automaton. And therefore the intersection is non-empty. Good. Are there any questions on this construction? No? Good. That's good, because later we're going to see similar constructions but a little bit more involved. So what is left is part B, and that's the next part. So the last part is that 3 implies 1. Yeah, so we just have seen 2 implies 3. We know 1 and 2 are equivalent, and now we prove that 3 implies 1. And in fact, I do the same thing as before. In fact, I prove not 1 implies not 3. So I prove the opposite. Good. So not 1 means assume TS violates E. Good. Then for pi hat being S0 to Sn in TS, the trace of this pi hat refutes E. This trace is L S0 up to L Sn. Thus, the trace of pi hat belongs to the language of A. Thus, there is an accepting run. Q0 Qn plus 1 of A for the trace pi hat. Accordingly, Q0 is an initial state, and we have that Qi has a transition to Qi plus 1 for L Si for all to n. And we know that Qn plus 1 is in F. Good. So now the reasoning is the other way around, right? Now I start with saying I have a bad prefix, then because of the bad prefix automaton, it needs to be accepted by this bad prefix automaton. So take this accepting run and try to, from that, to construct something which holds for the product. So then, by definition of this product operation, we have, and now we can combine the two things. So now I combine the string S0, Sn and these Qs. So similar as before, I have these S's, I have these Qs, and now I'm going to combine this. So now there is a run that says, okay, take all the first components, S0, take the second component, Q1, and from there I can move to the next state, S1, Q2. And now we get to Sn, I guess, to Qn plus 1. And this is an initial part fragment of this transition system TS with A. In particular, this last state satisfies F, so that means it violates not F, and therefore Ts times A violates the property always not F. And that was actually exactly the negation of 3. So all this work enables us to conclude that given a finite transition system, a regular safety property, how can you algorithmically check this? Construct the bed prefix automaton, construct the product, check in the product whether you can never reach a final state or not. And that can be done in linear time. Good. Product already. So here is an example. It's an example of a circuit and an example of a property of a circuit. So this is a circuit which is just one register, one input, one output. The output as well as the value of the register is the exclusive OR of the input and the register value. We have seen earlier in this lecture series that you can represent the behavior of such a circuit by means of a transition system. So here is a transition system corresponding to this circuit. I'm assuming the set of atomic proposition is just a singleton set Y. Then in those two states Y holds, and in those two states Y doesn't hold. Suppose I'm interested in the following safety property. The circuit will never output, there is a T missing here, two ones after each other. Suppose this is the property I'm interested in. Then it's not difficult to see that this is a regular safety property. So you have to construct the bed prefix automaton. Actually, this is the example that we have seen before. We know already it violates this property, because here Y holds and there Y holds, and there is a transition between these two. So it's possible that the output is high twice in a row. That's something we can see, but that's not the issue. How can you check this algorithmically? And here is the error indication. The bed prefix is YY. And how do you get this systematically? Well, systematically you get it as follows. You take this property, we construct the bed prefix automaton. And this is the bed prefix automaton. If I have 2 times Y in a row, we accept, because this is bad, and all other kind of behaviors are not accepted. So this is the situation. This is the transition system. This is the bed prefix automaton. Construct the product in the way I explained to you before. I'm not going to do this all in detail, but for instance, you see here that here you start in Q0. Here you start, for instance, in 1, 0. So suppose I start in this state. This state is labeled with Y. So I have to input this Y into Q0, which means I move to Q1. So the initial state of the product is 1, 0, Q1. And not Q0. Because if you consume already this first input symbol. So that's exactly what you see. The input, this initial state is 1, 0, Q1. There is another initial state that is 0, 0, labeled with empty set. You have to consider this as input to this Q0. So input this with the empty set. Empty set means take the self cycle. So the initial state for that initial state in my transition system is 0, 0, Q naught. 0, 0, Q naught. That's the second initial state. Okay. The rest of the construction is, as I explained before, this is the product. Now, what do we need to prove on the product? Thanks to this theorem, we only have to check, is there a state reachable that has a second component QF? Yeah, that's obvious, right? Because this is reachable, but also that is reachable, etc. This whole thing. So therefore, the property is violated. So this is an example of such a path. And that means that the error indication is this trace, or this execution, in fact, of this product transition system. And if I just ignore the second component, why is this? Yeah, I would like to give the user a counterexample on the original transition system, not on the product. So that it means it's very simple. You just erase the second component Q1 and QF, and that will be your counterexample. The counterexample will be the behavior of the circuit says you can move from the state 1, 0 to 0, 1. In both, the output is high, and this violates your safety property. So this is the counterexample. Okay. So you can construct this counterexample. If so, then you return yes, and otherwise you return no. I think that's pretty straightforward. And you can also get an error indication. How do I get this error indication in general? Well, this is the procedure. So you first construct this product. You're going to check whether the product satisfies always not f. If this is the case, return yes, because you can never reach such a thing, so then the property is satisfied. If not, then you compute a counterexample. How do you do this? It means that you're considering an initial path fragment in the product that looks like this. The final state, Pn, is an accepting state of the automaton. Then you retain, of course, no, because you found a counterexample. And the counterexample that you give back is just you erase the automaton states from this path fragment, and that gives you a path in my original transition system. And this is an example of a behavior of the initial transition system that violates the property. Good. Time complexity of this algorithm. To check whether this holds can be done by a depth-first search, just a standard graph algorithm. Yeah, you just look whether every reachable state is non-accepting. So this is linear. Linear in the size of this product. What is the size of this product? It's the size of T times the size of A. So it's the size of the transition system times the size of the automaton. So conclusion, checking regular safety properties is simple. You use finite state automata theory to represent bad prefixes, and you use a simple depth-first search on the product to check whether the property holds or not. On Friday, we're going to see that if the property is no longer regular, and then we're going to consider what we call omega regular properties, then automata accepting finite words that we use today are no longer sufficient. We need automata accepting infinite words. Is this surprising? Not really, because we know already that Leibniz properties cannot be refuted by finite words. Yeah, so in order to check, in particular, Leibniz properties, you need something more than only finite words. And that's what we're going to see next Friday. Thanks for your attention. Hope to see you back on Friday.